ice and matter. Every day, new discoveries are unlocking the mysterious, the mind-blowing, the deadly secrets of a place we call the universe. What would happen if our moon suddenly disappeared? Global tsunamis decimate coastlines around the world as ocean waters surge toward the gravitational pull of the sun. Sea currents shift, changing weather patterns and destroying food supplies. Eventually, Earth's axis tilts wildly, turning the poles into tropical jungles and the equator into frigid wastelands. New species emerge while others go extinct. Our planet becomes unrecognizable the day the moon was gone. The moon is a barren, lifeless rock, but it plays a surprisingly important role in the story of life on Earth. How important? Let's remove it from the sky and find out. Strange things start to happen almost immediately. People on the coast are the first to notice the change.
This would probably create something like a tsunami, a tidal wave, which would be very dramatic indeed.
It's well known that the moon controls Earth's tides. As it orbits around us, its mass tugs our oceans toward it, causing a tidal bulge on the side of the planet nearest the moon. And through a strange quirk of gravitational physics, it forms a second bulge on the side farthest away from the moon. Few people realize the sun also plays a role in governing the tides. But because it's 400 times farther from us than the moon, its gravitational influence on the oceans is relatively small, about 1/3 of the total effect. But with the moon out of the picture, the sun is now in control.
But with the moon up here, its gravitational pull is sort of pulling a dome of water up. There's a big sort of bulge. Then imagine you just snipped the cord and the water had to flow back out.
The water rushes toward the gravity of the sun in a massive global tsunami. The force of the waves depends on where the moon is in relation to the sun when it disappears.
If the moon vanished at full moon or at new moon, that's when the moon is lined up with the Earth and the sun.
The lunar tidal bulges would shrink to solar tidal bulges in the same spots, and the extra water from the lunar bulges would quickly flow to other parts of the globe. But there's an even more dramatic possibility.
If the moon vanished when it's at quarter moon, either first quarter or last quarter, then the moon's tidal bulge is not in the same place as the sun's tidal bulge. And so I expect you would see a very quick motion of Earth's oceans from the lunar tidal bulge to the solar tidal bulge.
Some experts believe this more drastic lateral shift in ocean water would blast coastal spots around the world. The powerful pulses would be similar to the 2004 Southeast Asian tsunami, except the waves would cause even more death and destruction, since they'd be worldwide. Two massive east-to-west and west-to-east waves would be initiated on opposite ends of the Earth. A seaside city like Miami would be pummeled by a 50-foot wall of water that would destroy most coastal buildings and sweep across the entire width of southern Florida, putting 9 million lives at risk. But with such a titanic shift of water, could there be other unpredictable results?
One can imagine that perhaps the east-west or north-south motion of that water could disrupt the currents. The Gulf Stream carries warm water from the Caribbean up to Great Britain, and it helps keep Great Britain a lot warmer than it otherwise would be, considering how far north it is. Climate is a very delicate system, and you tweak one part of it, and another part responds. And then one can imagine that food productivity and the overall way of life would be dramatically altered if it were cooler in northern Europe. The Sahara Desert is a great example of some place that used to be green and lush and now is completely a desert. Having changes with climate can really have impact on our survival.
But the biggest impact on our planet would be the changes to Earth's steady tilt, a unique feature that gives us our 4 regular seasons.
The thing that locks our planet's tilt to about 23.5 degrees so consistently is the presence of the moon that acts as a large stabilizer. If we don't have the moon anymore, we may get into a regime that's much more like Mars. And Mars, instead of being at a stable 23.5 degrees, goes through wild variations of the tilt, varying from maybe as low as 15 degrees on the low side, all the way up to something like about 75, 80 degrees on the high side.
Without the moon, our axis begins fluctuating erratically over several 100,000 years. The gravitational pull from other planets in the solar system starts wreaking havoc on Earth. Our stable seasons shift dramatically as different parts of our planet tilt radically toward the sun during some periods and away at others.
As soon as you get rid of the moon, you're stuck with this radical tilting of the axis back and forth, and therefore radical climate changes that don't happen today.
Earth becomes a very strange world as mankind struggles to adapt and survive.
If we go to a situation where we don't have that stabilization, those very small changes become very, very big. We may go to a situation where the ice becomes stable over the tropics. Imagine jungles and forests in Antarctica and ice sheets and glaciers in Central Africa. The tilt would vary on timescales of a few 100,000 years. These are timescales of ice ages coming on the Earth. We know how much of an impact that had, and humanity had a hard time adjusting to those changes as we came out of the last ice age.
It's very difficult to predict exactly what would happen to humans because we're not sure how rapidly we're able to adapt to radically changing environments.
And if our moon disappeared permanently, life in the sea and on the shore would be drastically transformed. Sharks would lose their hunting prowess, unable to track the schools of fish swarming above them in the moonlight. Crabs, used to mating at extreme low tides, become disoriented at the loss of lunar phases. Grunion, that lay their eggs during a high tide and full moon, suffer reproductive disruption. Even primitive aquatic plant life would be affected.
Many species will spend their evenings on the surface interacting with moonlight. The moon comes up, so the algae are moving up, and they're followed by all of the organisms that eat the algae and the organisms that eat them. So the whole ecology of the ocean is tuned to light. All of these organisms will be completely disrupted. None of their ecology will work because they won't have the usual sensing signals.
Millions of people would suffer from food shortages, and coastal economies would be devastated by the worldwide crash in marine life populations.
I would liken it to one of us suddenly waking up one morning and discovering we were blind or deaf. That would be a chaotic thing.
An Earth without the moon is a rudderless planet, highlighting just how critical this big rock is to sustaining life here. There are over 150 moons in our solar system, but Earth's moon is truly unique.
Our moon is unlike any of the other moons in the solar system. It is huge compared to Earth. It's about a quarter the size of Earth, and you don't see that in any of the other planets.
Because the moon is so big relative to the Earth, it's as if we're really in a double planet system. There's a crude way to think about the effect of the moon stabilizing this axial tilt of the Earth. If you notice, tightrope walkers will carry this long pole, and that gives more stability because there's mass out there on the end of the pole, and it's harder to fall off the line. So it's that same kind of thing, that the mass at a distance can affect the stability of the system.
But the moon has not always been by our side. There was a time early in Earth's history when there was no moon. A period when our planet was a strange place, with 8-hour days and a molten landscape too harsh for life. And then suffered the most violent collision in its history. It's hard to imagine, but there was a time when our Earth did not have a moon. Our planet was formed 4.5 billion years ago by accumulating and fusing large amounts of debris in the early stages of our volatile solar system. During that early period, our moonless Earth was a monstrous stew of flowing lava, molten rock, and liquid iron. Its atmosphere was filled with carbon dioxide, belched from the bowels of the Earth. Thick, heavy, and uninhabitable for life.
There was almost nothing on the planet. This was a nasty place to be. Lots of things were condensing. It was an extremely hostile place, even to rock chemistry. So the rocks were melted. Everything was a mess.
Our original Earth without its moon was an unrecognizable world.
The early Earth was a really hot place. In fact, that era of the Earth is called the Hadean, like Hades, because it was really hot. There was a tremendous amount of volcanism and a lot of impacts coming in. There was probably a lot of lightning and outgassing, both from the volcanoes and from steam.
The stability of our early solar system was not much better. It was created out of a huge disk of gas, debris, and dust that swirled around the newly formed sun.
Our early solar system was kind of like a roller derby. Everybody was generally going in the same direction, but there was a lot of chaos. There was a lot of clumping and accreting and things getting flung to the inside and crossing lanes to the outside. People all spilling over each other, mashing up in the corner. It was a real mess.
Without the moon, we can only guess at the Earth's early tilt and rotation rate. That would have been determined by the multiple glancing collisions from the innumerable asteroids and protoplanets that ricocheted throughout our early solar system.
If you kind of average over the solar system, you look at all the planets and the big asteroids and make a bell curve of rotation speeds, it looks like the typical rotation speed might be 8 hours, something like that. So we could make a guess that that might have been the likely rotation speed before the moon was formed.
Then, about 10 million years after our moonless Earth began taking shape, there was a massive collision. Now widely accepted by astronomers, the giant impact theory says that a Mars-sized planet collided at an oblique angle at 25,000 miles per hour with Earth. The impactor blasted more than 70% of the Earth's molten crust into space. A giant whirling arm made up of 5 billion cubic miles of blazing rock and light metals was launched into orbit around our planet. The gravity of the larger chunks began pulling smaller particles towards them. Within 1 year, it coalesced into our moon.
The only materials that were blown rocky material, and that's what the moon's made out of. And in fact, if you go to any other place in the solar system, for example Mars, or look at meteorites that come from the asteroid belt, there are certain ratios of the different types of oxygen. That ratio in other parts of the solar system is very different than what we see in the Earth. Now we fly to the moon, we get the moon rocks, we bring them back. They have exactly the same oxygen isotope ratio as the Earth. So that material came out of the Earth, and that fits this idea of an impact theory.
The energy released in the giant collision equaled a force of 6 trillion atomic bombs. That's 1,000 atom bombs for every person in Earth's current population of 6 billion people. The impactor planet that hit Earth was thought to have formed in an area of our solar system called the Lagrangian points.
These are regions 60 degrees either ahead of or behind the Earth, but at a similar distance from the Sun.
Debris can stay fixed in the Lagrangian points for tens of millions of years, locked between the gravitational influence of the Sun and Earth. But eventually, something knocked the impactor off its fixed course. That something was Jupiter.
Every time Jupiter passed by us in its orbit, it would be giving a little tug to this impactor planet. And each little tug wouldn't be very big. But if you think about, for example, having a car that's stuck in a ditch or stuck in a snowbank, how do you get that car out of the snowbank? Well, the way you do it is you rock the car. You push it a little bit, it comes back. Push a little bit more, it comes back a little farther. And this way, with a bunch of little pushes, you eventually free it. And that's exactly what Jupiter did to this impactor planet. And once it gets away from the Lagrange point, it's no longer stable and it's doomed. It's eventually going to collide with Earth.
After the giant cataclysm, the inner part of the whirling arm of ejected debris forms a clump that consists of materials from the impactor's iron core. That heavier clump recollides with Earth and is absorbed into our planet's center.
The giant impact was really the biggest thing that ever happened to Earth. What we have now is a core and a half. That makes our planet denser and our gravity stronger than it would be otherwise.
The larger molten core takes longer to cool than the Earth's original core would have. Heat is constantly pushed up and through the thin crust of the Earth, creating fissures. It's possible that this larger core helped create the sustained plate tectonic system that formed our continents, a unique planetary feature in our solar system.
As an example, Mars was much smaller, it cooled much quicker, and so it has no crustal plates.
Most critically, the collision knocks the Earth onto its current axial tilt of 23.5 degrees and speeds up its rotation from 8 hours to just 5 hours. Within a year, the Moon forms, roughly 14,000 miles away from Earth, significantly closer than its current distance of 234,000 miles.
You've got this immense moon in the sky, 15 times as big as the present moon. So think about this thing rising and rising and rising until it fills up a pretty big chunk of that evening sky. And imagine it being red because it's full of this molten lava around the surface. And imagine that looming over your head. It's mind-boggling.
The early moon's gravitational pull on Earth is roughly 200 times stronger than today because of its much closer distance. Though no oceans exist yet, the lunar tidal forces are 3,400 times more powerful. They lift and drop large crusts of molten rock to more than half a mile high twice a day. Our early planet's axial tilt stabilizes due to the moon's formation and its mass acts as an anchor. But the Earth's spin begins slowing because the moon's gravitation creates a tidal bulge around our planet's midsection, causing a drag on the Earth's rotation.
Let the Earth be this green balloon, and here's the moon. If the Earth weren't rotating, the tidal bulge would point directly toward the moon. But the Earth is rotating pretty quickly. So in fact, the tidal bulge tends to be a little bit ahead of the direction toward the moon. That means the moon's gravity is pulling back on the Earth's bulge a little bit, retarding its rotation ever so slightly.
But the tidal bulge on Earth also has a reactive force on the moon.
This tidal bulge pulls the moon ahead in its orbit. It's constantly trying to tug the moon faster. But the moon doesn't want to go faster in its orbit. Instead, what happens, if you imagine throwing a slingshot and swinging it faster, it wants to go out. And that's what the moon does. It goes outward because it's being tugged faster in its orbit. So gradually over the years, the moon is moving farther and farther out.
The complex gravitational dance between the two partners is now pushing the moon away from Earth at a rate of 1.5 inches per year. Over billions of years, the moon's recession has slowed the Earth's rotation from 5-hour days to our 24-hour day today.
The whole idea of this rotation of the Earth being influenced by the moon is a little bit like what you see when a figure skater is spinning, and when she pulls her arms in close and spins, she spins faster. And she throws her arms out to slow down. And this is all what the physicists would call angular momentum. But it's the same idea. As the moon moved out, it's kind of like throwing those arms out, and that slows down the rotation in the whole system.
But what if the giant impact had never happened? The changes to Earth would be even more drastic than if the moon now suddenly disappeared. Today, would we recognize an Earth that never had a moon? And would humans even exist? If the moon disappeared instantly, Earth would undergo changes like possible tsunamis, a shift in ocean currents, sea life extinctions, and eventual massive climate swings. But if the moon had never existed, Earth would be unrecognizable to anyone today.
Without the moon, life on Earth would probably look quite different. In particular, humans might well never have come into existence.
About 150 million years after a moonless Earth forms, 4.5 billion years ago, it moves out of its hot molten phase and begins cooling. The day is only about 8 hours long.
If we had an 8-hour rotation period, we'd have 4 hours of daylight, 4 hours of night. The nights would be totally black if we don't have a moon.
Once cooled, our planet is temperate enough to retain water. Heat escaping from Earth's core drives steam and carbon dioxide beyond the surface, creating a thick atmosphere.
Over a period of time, many years, all of that atmosphere would have kind of collapsed back out, and then as it cooled, the oceans would have formed in torrential rainstorms.
Icy asteroids continually pummel the planet, bringing in another large source of water. With a smaller, cooler molten core, there are probably no plate tectonics, and therefore no large mountains and huge ocean basins. Water soon covers most of the planet's more uniform crust.
We certainly would have a higher sea level than we have today, less continental area, and that would be a different world. Our blue marble would be even bluer.
Ironically, even with all that water, the early moonless Earth would have smaller tides. Determined only by the gravitation of the sun, they would be just 1/3 the size of our current tides. The range between high and low tide would remain constant throughout the year and would occur at exactly the same time each day.
And that means the intertidal regions would have been narrower, probably leading to less diversification of life and perhaps even impeding the progress of life from the oceans to the land. Because it's in the intertidal regions where creatures had to develop the ability to survive both in the water and on land.
With an 8-hour day, just 4 hours of light followed by 4 hours of moonless black, the early Earth spins 3 times faster than today. The winds howl due to the aerodynamics of Earth's quicker rotation.
Jupiter, for example, is a giant planet that spins very rapidly. It has a 10-hour spin period. And it's got ferocious winds in its upper atmosphere, hundreds of miles an hour, and incredible storms like the Great Red Spot, which has been around for centuries. Now, Earth probably would be spinning more rapidly than it is now, and that would generally lead to stronger winds and more violent hurricanes and other storms.
Early Earth's fast spin results in another important side effect.
The rotation of Earth's core, particularly the molten part of the core, is believed to be what generates our magnetic field. And so the Earth rotates 3 times faster, the magnetic field is 3 times stronger.
The enhanced magnetic field over the moonless Earth more effectively deflects high-energy solar flare particles towards the Earth's poles, resulting in larger, more spectacular auroras. But by blocking the solar flares, not as much radiation zaps life in the lower atmosphere, decreasing mutations that drive evolution.
Stronger magnetic field might have slowed the rate at which life evolved on Earth.
Without the moon, the developing Earth suffers intense climate volatility. Over many periods, each lasting several million years, the Earth's axis is pulled and pushed by the Sun and other planets. Without the stabilizing influence of the moon, conditions would have paralleled what happened to Mars.
What we've learned in the last 15 or 20 years is that Mars has a very unstable axis because it has no big moon. And when we look at Mars, and we can actually see on the surface of Mars geological features that formed under very different climate regimes when the polar axis was tilted over. On Mars, we actually see these features like the dry river channels and glacial deposits and other features, ice close to the equator. And so the big realization was, oh yeah, the climate has been changing on Mars, and this explains that we're seeing older features.
Like the red planet, a moonless Earth's axis would tilt wildly, turning our planet topsy-turvy.
Our axis, over a period of millions of years, would wobble chaotically. It would sometimes be vertical, it would sometimes be close to horizontal. When it's vertical, then the whole Earth might be kind of a tropical paradise. When it's horizontal, you could actually have the poles pointing towards the sun and the poles actually getting jungles. So you would see very big changes in Earth's climate as a result of this chaotic wandering of Earth's axis. And this would make it more difficult for life to flourish because it would constantly have to adapt to different conditions, to ice ages and to extremely hot ages.
So what would life on Earth look like today if we had never had a moon? Short days, high winds, and other changes could produce a freakish world with creatures that look like they're straight out of science fiction. The moon was formed billions of years ago when a planet-sized asteroid crashed into Earth. But what if that violent collision never happened? If the moon never came along to stabilize our planet, Earth would be an alien place. The spin of early Earth was very fast, with about 4 hours of daylight followed by 4 hours of darkness. Over billions of years, the lengthen that 8-hour day to 12 hours. But this is still twice as fast as the current Earth spins, which makes for some extreme weather, including devastating storms and high winds.
If the moon hadn't formed, you certainly get a wildly different environment on the Earth. With a faster turning Earth, you get more jet streams, you get more turbulence probably, maybe bigger storms, more lightning because of the friction of the different masses of air moving.
In some places, the winds could reach 100 or 200 miles an hour. There would also be stronger hurricanes, and the Earth would have larger waves battering the coastlines.
And without the moon's stabilizing effect, the rapidly spinning Earth tilts back and forth. Over hundreds of thousands of years, our planet suffers the ravages of ever-shifting climate because of the erratic changes in axial tilt. As different regions are blasted by heat, then covered by ice again and again. And without the moon, there is another layer of axial instability. Even though today's Earth is stabilized by the moon, there is still a wobble to the Earth's rotation, known as precession.
Earth's tilt is 23.5 degrees, but over a period of 26,000 years, it goes through conical variations like this.
And if the moon had never formed, this wobbling would be much more unpredictable.
If we didn't have the moon, the Earth would precess much more slowly, and this is one cause for chaotic variations in the axial tilt. A slower precession of the Earth would lead to a much more unstable axis of rotation for the Earth.
Without the moon, Earth's axis today would be like the slower spinning top, precessing, gyrating, and wobbling in ever larger conical circles.
Right now, 26,000 years, very stable zone. You get it going slower, so it's maybe 40,000, maybe 50,000, maybe 60,000. Then you hit the chaotic range, and then everything goes wrong.
With the more forbidding and shifting climate, evolution on a moonless Earth varies between bursts of adaptation and violent extinction. Bizarre life forms mushroom. Plant species are vulnerable as they don't have the mobility to stay ahead of speedy climate change. And complex life forms like humans probably wouldn't stand a chance at all.
The variations in climate would be extreme and rather rapid, and it would probably make it difficult for complex creatures to evolve, because most complex creatures can't evolve very quickly to changes in their environment.
Instead, primitive organisms would predominate and endure.
Bacterial life is able not only to adapt more quickly, but also to withstand more extreme environments. We see bacteria under the deep ice cores of the Antarctic or Greenland, and we see bacteria that live in steaming, boiling pots in Yellowstone.
If complex life were to evolve, it would look very different due to short days, high winds, and other features of a moonless Earth.
It would be much more hostile than it is now. You would see that all of these winds and all of the noise and all of the clouds moving from water to life on land would be very tough. We might see shorter lifespans because things are going on faster. During the day, there will be a limited time to metabolize and gain energy and do things. Organisms would have to be a little more clever.
Evolution would favor short, stout creatures and plant life that could withstand ferocious hurricanes. Jungles wouldn't exist, since they need wind barriers to flourish. And there probably wouldn't be any creatures swinging from branch to branch due to stubbier plant life and high winds.
I would expect that creatures generally wouldn't be as tall because they'd have a harder time holding themselves up. and trees with shallow root systems wouldn't become very tall. Palm trees, for example, probably wouldn't survive too well.
The constant gusts would push other adaptations.
Sailing, maybe membranes that let you take off and leap through the air.
And the perpetual gale-like conditions would create an exceptionally loud planet. If animals made noises to communicate, they'd have to be very different from the constant shrieking wind sounds.
The use of sound at wavelengths that are not the sound of the background noise. If you have a receptor that just zeroes out that noise, we might be able to speak like this and be heard perfectly. We might all be sopranos and have ears tuned to a different pitch.
Or more visual cues might be developed to cut through the audio overload. Creatures might develop extra limbs to not only shield themselves from the wind, but also use their appendages to communicate, like sailors using semaphore signals.
Perhaps speech would not develop, so maybe other forms of communication, whether color changes, expression changes, hand languages, who knows?
Even today, many of Earth's beings, such as fireflies, squids, krill, and jellyfish, communicate by changing their body colors. Because of the dark nights, creatures might also develop enhanced vision and sensory systems, similar to the night vision goggles and infrared displays used by the military.
The interesting possibility is that life might be able to develop sensors that were so good that they could actually sense starlight. And this would be something colossal.
It looks and sounds like a rough and too tough world, unfit for human habitation. Luckily, when the moon formed, it created the conditions for people to develop and prosper. But our moon is also moving farther away from Earth every year. Does that mean there will be another time in Earth's future without the moon? 4.5 billion years ago, the young Earth was a hellish, molten place, unfit for life. So then, how did a violent collision by an object the size of Mars, soon after the Earth's formation, create the conditions for the complex life we're part of today? The body blow to Earth knocked our planet to its current tilt, and the formation of the moon kept it there.
The mass of the moon out there, what it's done is it's prevented the tugs of the other planets from causing the Earth's tilt to change too much. So it's provided a real stabilizing effect on our climate because of that.
The collision also created a chain reaction of forces that set the stage for life. When the iron cores of the two planets combined, it created a larger core for the new Earth. The collision also knocked off much of the Earth's crust. This combination, with large amounts of heat pushing up from a giant core through a thin crust, likely created the conditions for sustained plate tectonics. The movement of these plates formed mountain ranges and deep basins, and the resulting volcanic activity spewed out the gases that created our atmosphere. Water eventually settled in the basins, creating oceans, leaving continents of land above. But life still had a tough time getting started in the early days of Earth.
For the first 500 million years of the Earth's and the Moon's existence, they were bombarded by debris that was still finishing up the formation of the solar system. So even if primitive life, microbes and bacteria, had formed in the first few 100 million years, they might easily have been wiped out by these giant things crashing into Earth. Now, we have evidence for life dating back to 3.8 billion years ago. That's shortly after the end of the era of heavy bombardment.
By then, due to tidal friction between the Earth and Moon, the Moon had moved slightly farther away from Earth, and Earth's rotation had slowed to roughly a 10-hour day. But since the Moon was still much closer than today, the tides in Earth's early oceans were humongous.
The tides went way inland and poured back out to sea. Twice a day, you'd get a big gulf of water in, and when it drained back out, it carried a lot of minerals and soils and other parts of the Earth's crust back out to sea with it. So there was this constant erosion and scrubbing of the land. Certainly a unique environment that might have been just right for life to develop.
The area between high and low tide, known as the intertidal region, was enormous. High tides would rush hundreds of miles inland, then back out a few hours later. During the low tides, molecular strands began forming in some of the endless miles of tide pools.
What happens when water evaporates? The H2O molecules go away and everything else is left. So the organic sludge in the pool gets more and more concentrated as the water evaporates. So this was the idea that life formed in these little pools.
Around 570 million years ago, almost 3.9 billion years after the giant impact, Earth's ocean life begins moving on to land, giving birth to complex species.
The bigger the intertidal regions, the greater the resulting diversity of life, because you can have species that live in these environments that are sometimes exposed to the sun and sometimes underwater.
Over billions of years, our Earth seems to have reached a perfect equilibrium that has allowed for the evolution of a diverse, intricate, and fragile ecosystem.
There are some climates that are too uniform, no seasonal changes and so on, and don't lead to life because there's no environmental stress. And on the other hand, climates that are too variable, where the seasons are changing all the time, you're getting hit by an asteroid every million years. Planets like that would probably try to form life, but they couldn't get it going because things would change too fast. So maybe there's a situation that's just right in the middle, and maybe the Earth-Moon system is somewhere in that range, which has fostered not only formation of primitive life, but the evolution of that life into folks like us.
But though our moon stabilizes things, it continues to recede from us at a rate of 1.5 inches per year, while it slows our spin. Scientists estimate that we're adding 2 seconds to our day every 100,000 years.
A billion years from now, our days might last 26 hours rather than 24 hours, which is great if you're a procrastinator like me.